Hi, everyone. Thanks for joining us for this talk. My name is Matt Norman. I'm in the National Center for Computational Sciences at Oak Ridge National Laboratory, and I'm going to be talking today about exploring performance and readability with the miniWeather mini app. You can see on the slides here, there's this link, and the slides will be provided for you, where you can go to the miniWeather repo on GitHub. So first, I want to acknowledge funding from the OLCF and from the Exascale Computing Project, which has contributed, at least indirectly, to parts of the work done for this talk. This work was done in exploration of aspects we can use for our climate modeling project. So I just want to start by saying accelerator programming is messy. There are a lot of options that we have available. There are a ton of hardware backends, and even within a given vendor, you have a lot of different properties for different versions of graphics cards. There are a lot of languages that we're using. There are a whole lot of specifications like OpenACC, OpenMP, and the two versions of OpenMP. We have libraries and a lot of compiler options available to us. And the route that you choose will limit the compiler options, the languages, and the hardware that you can use in the back end oftentimes. So most of us, well, many at least, have a large amount of code in our applications that are structured mainly for CPU performance. And there are no optimal solutions here. The trade-offs are pretty messy, and regardless of what we choose, it will require quite a bit of work. So in this talk, I do not want to tell you what approach you should use. I think context is everything in that area, and we just don't have time to explore, which route you should choose in a given context. I don't even really want to say why I've taken the approaches that I've taken. I just want to take a look at whatever approach you've chosen. What does performance, portability, and readability look like? And we're going to do this in a limited context. Again, this is in the miniWeather mini app, which is a relatively small application, but it's a little more interesting than a matrix vector multiplier or amenable fractal. It simulates weather-like flows with very simple code. I think the code that is actually that the user interacts with is only a couple hundred lines long. It covers a lot of language and parallelization strategies. So we have Fortran C and C++. We have MPI, OpenMP, CPU threads. We have OpenACC, OpenMP offload, and do concurrent. And hopefully once we have MD-span in the C++ standard, we will also have standards-based parallelism in C++. There are a lot of things I don't cover, including DSLs, Julia, Python, and a number of other things. And I didn't have easy access to the Cray compiler, unfortunately. So when we look at the performance results, you won't see that there. It's just because I didn't have easy access to it in preparation for this presentation. So first, I want to start off, there is an aspect here that we're going to focus on somewhat that's portable C++. I just want to say portable C++ libraries like Cocos and Raja, they're just libraries. They're not language extensions. What they do is they encapsulate loop body code and they pass it to a hardware backend. They can launch it on vendor hardware using vendor languages like HIP, CUDA, SYCL, OpenMP, and so on. And the C++ portability library I'm using is called Yet Another Kernel Launcher. This is kind of an in-house C++ library for the E3SM MMF code in the Exascale Computing Project. It currently supports the 3 GPU vendors and CPU threads with OpenMP. It allows highly Fortran-like code in the back end. We have multi-dimensional arrays that behave just like Fortran arrays, and we have a limited Fortran intrinsics library. You can write C-style code if you want as well. And it has an automatic transparent pool allocator for all device allocations. So frequent allocations and frees are very, very cheap. That'll play into some of the performance results. And I just want to say it's not necessarily representative of these C++ portability libraries, but it is hopefully small and simple enough that if you check out the repo, you can actually see what's going on clearly under the hood. With that, I'll go ahead and move on. This is an example of Fortran-style use of the ACL C++ library. I won't go over everything here, but this is calculating the maximum stable time step for a shallow water model, for instance. But we pass in our arrays, height, U and V, and you can grab the dimensions like an assumed shape array using the size intrinsic. We have epsilon and a number of other intrinsics. When you allocate an array, it is similar in nature to the Fortran allocate statement at least, except we have this label here for debugging and profiling. And the biggest difference is the do loops and the parallel for syntax are quite different. That's by far the biggest difference, but the loop body code is identical to what you would see in a Fortran model, for instance. And if you want a reduction or something, we have the Fortran intrinsics, min val, max val, and sum. That's just giving a flavor of what it looks like in terms of readability for someone who comes from a Fortran background. So let's jump right into performance, looking at the different options we have here. And a lot of these comparisons will be C++ and Fortran, but even within Fortran, we want to look at all the options that we have for directives and standard space parallelism, at least the ones that I had access to. And again, the GPUs that I'm running on, they're all NVIDIA in this case. And I didn't run on a ton of different NVIDIA hardware. I just ran on the ones that I had direct access to. So what we see here is the C++ and Fortran GPU performance on the whole is about the same. C++ is about 25% better in single precision and 25% worse in double precision. And I've tried to dig into this more and haven't found any red herrings yet. Well, that's not the right term. I haven't found any obvious reasons yet. For the GNU compiler, I think they're still developing their performance strategies for OpenMP and OpenACC directives. Their OpenMP assigns 255, the max amount of registers per thread, to all kernels, so naturally the performance is quite poor for those. And the GNU OpenACC currently assigns more registers per thread than the other languages and compilers do, which it's not always a bad thing to have more registers, but once it reaches, a high number, say more than 64 or something like that, then you can really start to damage occupancy to the point that you'll notice it in the overall runtime. The NVHPC compiler has, well, to my knowledge, the only do concurrent implementation. Cray might have one, but again, I didn't have access to that immediately. Do concurrent is a very interesting one, and I want to dig into it a little more. The kernels are actually a bit faster than all of the other options for the NVHPC compiler, but you'll see that there are some memory issues and some kernel launch latencies that get exposed that actually make it slower overall. And finally, I'll just say C++ YACL code uses far fewer registers than all of the other options in Fortran. Again, that doesn't always mean better performance. You really want to use registers because they're necessary for floating point computations, and they are quite fast if you can leave data in them, but you don't want to use too many. But that was an observation that I've noticed that may have some impact on the performance. Zooming into the do concurrent performance with miniWeather, on the top, you can see the OpenACC overall. All the kernels are running quite close together, but on the do concurrent, we see these big gaps. And in this case, they're not associated with kernels, but there are some cases, I ran it over and over again with profiling. Sometimes it's associated with really long kernels, sometimes it's not. My hunch is that this is related to the use of unified memory, and there's just a couple of hiccups that are showing up, and I'm not entirely sure why, but it would be really nice to look into it eventually. Do concurrent is not aware of multiple memory spaces, so it kind of inherently has to use some sort of memory, managed or unified memory. The other thing is there's no async construct with parallel do. And so when we actually look at the launches of these kernels, you can see the OpenACC is launching all the kernels async. And so you're actually hiding launch latencies with kernel execution. And everything's packed together quite nicely. And we don't have any real launch latency gaps in the profile, but for parallel do, again, my hunch is because there's no async specifier, they're not overlapping properly to reduce launch latencies. So just in general, a note on the in-language standard space parallelism. I don't know what to call this because technically OpenACC is also a standard and standards-based. But it would be ideal to use the in-language standards-based parallelism, in my opinion. I think for some projects, it may be a bit underspecified for some people's needs. In our case, we're very latency sensitive, so asynchronous execution is important. Moving data between different data spaces, memory spaces, is important to be able to do manually for performance reasons for some applications. And it's not clear that hierarchical parallelism has a clear expression in the language parallelism. And if you were to nest these, it's not clear what they should offload onto. There would be no guarantee. It would be compiler dependent, which is somewhat similar to how OpenMP offload is working today as well. OpenACC seems to have this kind of agreed upon what gang worker and vector mean, but that understood agreement doesn't seem to exist in the other expressions of parallelism. But there are plenty of projects, I believe, that could use it efficiently today, and it's quite nice to not have to rely on something outside the language specification. And I would also say, just remember that accelerator programming is pretty niche overall, and it's not clear if the language standards even should bother addressing these aspects that I mentioned above, and there are probably other things that they could address. And I'm really hoping to get a miniWeather version that uses C++ standards-based parallelism. And Jeff Larkin has kindly created a pull request that does it so far. But before we merge it in, I'd really like to have ND span so we can have an expression of a multi-dimensional array so they can look somewhat similar to the other C++ approach. So CPU performance is really the interesting one. I don't have time in this talk to go into every aspect of it. All I'll say is that I tried my best with vectorization flags and compiler flags. I ran two versions of the Fortran. One is I would call optimal, that uses explicitly sized arrays and does not allocate during the runtime. The other one will allocate frequently during the runtime and use assume. And you can see this harms performance quite a bit. I would also argue, though, that using this approach in Fortran is the least bug potential and also the clearest to read because your variables are only scoped where they are needed. But clearly, the performance is quite badly impacted. The other thing I'll say is that when you turn on all the bells and whistles in the compiler, dash fast, turn on the vectorization, everything you can, C++ is generally worse than the Fortran compiler, sometimes significantly so. This will not be a surprise to a lot of us. But if you use a pack structure where you take every individual operation and try to really explicitly force a vectorization loop, you can actually get very similar performance to the best case Fortran. So the C++ code can run similar to Fortran, but you really have to use a lot of effort to make sure that it vectorizes properly. Again, I have these in the slides and I encourage you to read them, but I would like to make more time for questions and we can go back to these slides for questions at a later time. I want to talk briefly about readability in the remaining time for the talk portion, and then we can discuss the questions that you have. And I strongly encourage you, please ask questions. We do have time for that. So for readability, I'll just say it's highly contextualized. Some people are expert C++ programmers and they like indirection. They like to have to search for code and they like really verbose long expressions. Some are more domain-oriented scientists that code, say, in Fortran, and they really want to see everything be sequential, for instance. They don't want to have to hunt for code. What I would say is that you should look at your project and just pick something that everyone in your project can understand quickly and make innovations on. We want minimal, clean syntax with minimal concerns. The asterisks in C make me go blind. I'm not a big fan. And template expression should at least be reduced to something that is a little better to look at face value. I would say use abstractions sparingly if you can. If it reduces code duplication significantly, I think it's definitely worthwhile, but we should always question whether abstraction and indirection are necessary there. We just want domain scientists, non-computer scientist experts to be able to work productively in the same code that we're running in performance production runs. Again, it'd be nice if variables could be scoped to where they're needed only. Not a big fan of globals. Function calls should express read-write usage of all the variables wherever they can. And again, just documentation at all levels, as much as you possibly can. It just really helps other people come in externally from the project and get spun up quickly. As far as barriers to productivity, I would just say the Fortran specific issues is get rid of these static lifetime variables, module scope variables. You just don't know which routine is changing those variables when. I get that it cleans up the syntax, but that convenience leads to a lot of danger. If you explicitly size your arrays, Fortran trusts what you say they are, but if you make a mistake, your bounds checking no longer works, for instance. So it just makes the bug potential quite high. But again, we saw earlier that when you do these things to make the code easier to follow and understand, it harms performance. So, either we need to figure out how we can improve this in the compiler by, say, allocating everything closer together if we can to reduce the TOB misses. But I think there are aspects where we can pull this closer together. The C++ specific issues is the language features overall seem to almost encourage overuse of indirection and abstraction. There are so many features in C++, and it can just lead to messy implementations overall. It does have reduced performance compared to fully optimized Fortran, which we can overcome with explicit use of, say, packs. But using pack data structures, I believe, obfuscates really important aspects of what the code is doing. I'm not sure it's the most productive choice for all projects when it comes to making the code productive for all the scientists on the project. But I also think that compiler improvements can really help bridge this gap without having to go that extra mile to use pack data structures. It's not just restrict on the pointers, for instance. There are compiler flags that can just assume restrict on all pointers, and it still doesn't really help. I will say, if you use a really old version of some of these compilers like GNU and Intel, the performance is far, far worse than it is with modern versions. So the compilers have made significant improvements. But I think if we can continue to do that, it will help kind of bridge this gap of writing readable C++ code without having to really work hard for vectorization. If you want to take a quick look at what these pack objects look like in the miniWeather code, again, we have a pack that's some sort of SIMD length that you have to know at compile time. It would be 2, 4, 6, or 8. In general, all of the arithmetic, like so what you see down here in the stencil, first and third order derivatives, this looks just fine because each of these operators is actually looping over some chunk of the array. But whenever you have if statements or different behavior between different elements of the pack, you end up having to iterate over the pack. And the syntax gets really messy. And again, I'm just not certain that I would want to expose a domain scientist to that sort of syntax. So I'll leave with this last slide of summary. What I'll just end with is when we're trying to strive for portability overall and productivity in our codes, we should expect the computer scientist experts to have to tone down their expertise and their expression of complexity in the user-facing code. We should also expect domain scientists to have to learn a little bit more to understand what they're doing and where it impacts performance. And I believe we should expect to have to sacrifice some performance to make a code productive and readable overall. I think these are all reasonable things to expect. But again, every project has their own sort of culture, and you have to choose what's right for you. But hopefully this gives you a taste of no matter which one you chose, aspect you chose, you know, the performance can be quite good overall. The GPU performance all seems to be pretty good overall. I think the GNU compiler will catch up just fine in some time. But, you know, directives can be very readable and very performant, but so can C++. The CPU performance is really where everything starts to get a little bit messier. And it's just, you know, we have to think more about it in that context. I also think that if you want to support two different codes, say one in the original Fortran that works well on CPUs and one in C++ that you can express well for GPUs, if you were to make that choice, as long as those codes can look very similar, I think it would probably be okay because you can use testing to determine when they diverge. You can mirror a change between the two code bases quite easily. But ideally, you really want to just support one code base if you can. Thanks for your attention.